So I'll just give you a little bit of background to situate what I'm doing today. So my work primarily is in the theory of algorithmic randomness. And I, as a person who works in the field, primarily proving theorems, I'm interested in working on how algorithmic randomness informs, say, probabilistic computation or randomness extraction, or random objects like trees and closed sets of stochastic geometry. But then I have some interests philosophically in trying to understand what even the kind of core results in this field tell us about the concept of randomness, and how applications of this into other areas of mathematics can illuminate more classical notions of randomness, but also illuminate things like the incompleteness phenomenon and questions in, say, the philosophy of probability. So I have broader conceptual interests as well. So this really fits into that second line of research where I'm trying to understand what are the deliverances of a kind of classical theorem in this field. And so this is what is Chaitin's Incompleteness Theorem. And this is based on a paper that got published last year in the Notre Dame Journal of Formal Logic. So all the details can be found there. If you're interested, I can send you the paper after the talk. So with that background, let me collapse my, move my, these Zoom windows kind of get in the way. There we go. Okay, so in 1974, there was this paper early in the development of algorithmic randomness, or the algorithmic information theory, as it's sometimes referred to, really started in the mid-60s. So in 1974, Gregory Chaitin has this paper that he proves this really interesting incompleteness theorem. So the paper is called Information Theoretic Limitations of Formal Systems. And the incompleteness theorem is very unlike, say, the Gödel incompleteness theorem or any techniques that have been used to prove incompleteness results up to this point. And Chaitin has gone on to do a lot of writing. He's written many books and given many talks and papers where he tries to advertise the significance of this and other kind of related results, and often in a very, I would say, provocative way. So he'll say things like his incompleteness theorem, which I will write as CIT for Chaitin's incompleteness theorem. He's written in one paper that this shows if one has 10 pounds of axioms and a 20-pound theorem, then that theorem cannot be derived from those axioms. Okay, that sounds really remarkable. Like, how do we put weight on axioms and theorems? And is it really the case that the relative weight of these things have some sort of formal consequences or formal bearing? And elsewhere, he says that his result shows that the incompleteness phenomenon is much more widespread and serious than hitherto suspected. All right, this is post-Gödel, post-Turing, and subsequent work by unpacking the incompleteness and undecidability. Chaitin comes along and proves this new result, and maybe somehow this so he claims gives us insight into how widespread, or even they might say the source of incompleteness, or a source, the source. Okay, so those are some, I would say, pretty bold claims. These have been subjected to much criticism, and so by and large, in philosophical work, often you don't see, I would say, open and shut cases or devastating arguments, but the literature that treats these claims, which aren't made super precise to begin with, any attempt to make them precise are shown to be lacking. And so we see this claim about the amount of information in a form of theory in, say, before the wave of new interest in work in algorithmic randomness in, say, the early 2000s, we'd already seen Michael van Lumbegen, Panu Radikainen, Torkel Franz, and all give really strong refutations of the measures of amount of information that Chaitin presented. And I'll say a bit about those in a little bit. And then this claim about how widespread and serious the incompleteness phenomenon is, as shown by this theorem. There's a paper in Principia Mathematica by Don Fallis in '96, and then Panu Radikainen has multiple papers on this as well. Really push hard on and really, I think, decisively refute Chaitin's claims. So given what I think are pretty convincing refutations, why should we revisit this theorem? And I have two reasons for doing so. So one is that there is relatively recent, 2013 work extending Chaitin's theorem, which I think is really underappreciated. It's I'll say more about that in a little bit. It's due to Bienvenu, Shen, and a few other authors on the axiomatic power of Kolmogorov complexity. It was published in the Annals of Pure and Applied Logic. That is a nice overlap between computability, logic, and randomness. And they prove some really great theorems that I think by themselves are compelling. But one could pull from that work or extract from that maybe a sharpening of Chaitin's claims that could potentially vindicate them. In particular, there's this the thought that Chaitin's undecidable statements, the statements that he identifies as unprovable, have some sort of priority over other undecidable statements, at least in the context of arithmetic. There may be something to that, right? So that's something that I want to see how we might try to work out that claim. And despite that, and these results I think are really, really interesting in their own right, that argument for priority doesn't succeed. So I find in this newer work the potential to sharpen and maybe support Chaitin's interpretation. Ultimately, I don't think that's the case, but I think it opens up new lines of formal work that we can explore. So that's one approach, one reason why revisiting this is worthwhile in light of new work. And then in second, I want to give an alternative account of what the Chaitin's theorem, the significance of it is. And this is part of the broader project of trying to understand, right, what these theorems tell us about the concept of randomness or about formalizations of randomness. And in particular, I'll just read these bullet points here. I don't think that, and this is just really not me echoing what has been established, Chaitin doesn't provide new insight into the incompleteness phenomenon. But I think that there's something else that is lacking in the literature of a positive account that his theorem shows something about like a formal trade-off or cost that comes with defining and working with a strong notion of randomness. So I have to specify what I mean by strength here, but there's a kind of a meaningful way to understand what it means for a definition of randomness to be stronger than another. And as we vary this notion of strength, there are going to be other consequences. We may lose certain desirable properties of the resulting notions of randomness. Okay, so this is there's a formal trade-off between the strength of a definition of randomness and certain properties we might desire of a definition of randomness for other purposes that we might have. Okay, so that's the last part of my talk. I'll try to say what those are. And this is really kind of an instance of a work that I've done. I've got a paper in Philosophia Mathematica last year, or I guess earlier this year, where I'm trying to understand, for instance, what the statements about the equivalence of different definitions of formal randomness, what they show us, and I'm giving a pushback. I'm pushing back against some other similarly overblown statements. So I'm really wanting to do more than just negative work of knocking down other bad interpretations, but give positive, constructive. Not constructive in the logical sense, but at least, saying that there is something that we can learn, that's something that's informative. Okay, so I'm going to give some formal background because I don't assume that anybody here is familiar with the notions that we'll be working with. I'll talk a little bit about the proof of Chaitin's theorem, which is really remarkably concise and fairly easy to communicate. I mean, easy, or just doesn't require hours of background information. And then I'll say a little bit about the interpretation that Chaitin has offered before. And that will allow us to then see how we might sharpen or make further, precify that interpretation in terms of more recent work. And then I'll give my own alternative interpretation. And of course, if you have questions along the way, please feel free to stop me. And I don't want to, I'd rather you understand what I'm trying to do here than just get through a bunch of slides. Okay, so the driver behind the main concept that gets used in the proof of statement and proof of Chaitin's theorem is this notion of Kolmogorov complexity of finite strings. So when Chaitin is working in 1974, Kolmogorov's paper came out in 1965, and Chaitin made significant contributions to modifying Kolmogorov's definition so that we can extend the notion of randomness to infinite objects. But really, for what we're doing now, we don't need any of these modifications. We just need the, I would say, vanilla notion of Kolmogorov complexity that Kolmogorov introduced in his 1965 paper. Okay, so this is a notion of complexity for finite strings. They could be binary, but they don't have to be. It's easier to make it that way. And this is a notion from which we can define what it means for a sequence to be random. Okay, I should say a finite binary string to be random. I'm not going to talk about infinite sequences at all today. Okay, so how do we do this? Right out the gate, let's fix a Turing machine M. And so I'm going to think of my Turing machines here as functions that map binary strings to binary strings, finite binary strings to finite binary strings. Now, suppose I would like this machine M to output a given string. Since M computes a computable function, the process of outputting the string is something like it's constructing the string, right? It's going through algorithmically, reading some information off of its initial tape, and as it's doing, running along, routines and subroutines, it's recording the bits of sigma on the output tape. So we can view this as a construction of our string sigma. So any string that I put on the input tape that yields as output the string sigma as, like on the output tape, we can think of this as like a blueprint for the construction of sigma. I'm using my machine tau with some initial instructions given by, my machine M with something like initial instructions or information given by tau, and the output is my string sigma. Often in our literature, this is tau gets referred to as a description of sigma, but that's a really loose use of description because it's not just a description like my favorite string, but something like a description that allows me to pick that string out of a lineup of all other strings, right? It's a description that's only satisfied by the singleton of my string there. So I tend to avoid using description talk, at least from a philosophical point of view. I would say something like it's a blueprint for the construction of my sigma. I'm trying to convey to you instructions for how to reproduce that string as that string, and not just some loose description of it. Okay, so giving you some examples. Suppose my string has some regularity, some sort of structure to it, then it should be easy to construct in some way. Right? Well, what does that mean? So for instance, suppose my string sigma is 50,000 zeros. Then I might be able to feed my machine the instructions that say print 0 50,000 times, and then the expression 50,000 in my program is not, I'm not actually writing 50,000 zeros. That's like log of 50,000. It's a much shorter way of conveying that information to you. And so from a fairly short input, print 0 50,000 times, you have now reconstructed this string of 50,000 zeros. Similarly, if my string is 01 repeated 25,000 times, that is also just slightly longer of a set of instructions to reproduce this string sigma. Or if sigma is, say, the binary expansion of the decimal part of pi, which is apparently these values here, there are really efficient algorithms for estimating or approximating pi to any precision we want. So if I wanted to output the first 50,000 bits of pi, the decimal part of it, in binary, there's a way to do that requires much fewer than 50,000 input bits. Okay, so then similarly, you would suspect if regularity somehow corresponds to being obtained by short inputs being constructed by kind of compressed blueprints, if a string lacks regularity, it should be difficult to construct. If I toss a coin 50,000 times and I say to Marcus, I would like you to reconstruct the output of my experiment of tossing my coin 50,000 times, with all likelihood, I'm not going to be able to give him a set of instructions more concise than me just reading one bit at a time, because there's not enough structure to be able to capture that information. So no shorter inputs should allow me to construct my sequence. So the complexity of sigma is here in Kolmogorov's approach determined by the length of the shortest input given time my machine that yields the output sigma. And moreover, not stated here, regularity of my string should correspond to having a lower complexity, and the lack of regularity should correspond to having higher complexity. That's really what Kolmogorov's idea was. So let's formalize this. I'm going to fix here any Turing machine, and you might bellyache about or object about this in a second. That's fine. We'll get around that. I wanted to find Kolmogorov complexity of a string sigma relative to this machine. So what I'm going to do is I'm going to look at, so I'll use this subscript, I use C for Kolmogorov complexity. This subscript M here tells me what machine I'm using. It's the minimum length of an input given to this machine that yields sigma as an output. Now, if my machine, for whatever reason, doesn't output sigma, then I want this complexity to be approximable from above. So by default, we'll set this initial value to be, if it doesn't yield it as an input, then we'll say the complexity is as infinite. Now we won't say anything about that in this case here. And you'll see why in a minute. One worry is that for many machines, this doesn't appear to be a very meaningful notion. Maybe my machine only has a limited range of calculations it can perform. Maybe that machine is the identity machine that just takes an input and yields the same string as an output. There's no compression going on there at all. It's just copying the input and yielding the output. So I would like to be able to do something more robust that's takes into account any constructive procedure for yielding my string as an output given an input. And so here we'll use universal machines. Already an insight that Kolmogorov had in that 1965 paper. So how do we do that? Well, one way to do that is let's effectively enumerate all of our Turing machines, right? If you know a little computability theory, you know that each Turing machine has an index. So we can put all of our Turing machines in order by their index. And now I'll define a universal Turing machine in this way on strings. It will, if I'd like to simulate or copy what the ETH machine does on input sigma, I will have my universal machine on input, which is a block of, say, E1s. Okay, so my ETH machine, I have E1s followed by a 0, and that 0 separates the coding block from the string that I care about feeding to this machine. So the universal machine will copy the ETH Turing machine with a little bit of overhead. So here, E plus 1 extra bits that it needs to incorporate into this computation. Okay, so that's one way. It's a very standard way to define a universal machine in this setting. There are other ways to produce universal machines. For instance, using a different enumeration of all of these Turing machines, or using a different mechanism for coding my machines instead of using, say, a block of E plus 1 bits. This will have some bearing on our discussion. Often in the field, we gloss over all of these little differences, but they have some they have some bearing on the broader implications of the theorems that we're going to consider. Okay, so let me now define Kolmogorov complexity with respect to a fixed universal machine. And in the literature, it's very common to just drop the subscript. This is like some sort of parameter free, although it looks like we've chosen a universal machine. Well, okay, let's ignore that for the moment. Once I've picked my universal machine, now I look at the shortest input tau that yields sigma as an output, and that's the Kolmogorov complexity of sigma full stop. Okay, so now U is fixed, and we'll just say we'll define complexity of a string with respect to that universal machine. We don't even need to quantify over which machine we're using. But now, again, we want to be careful. We want to be careful. How can we justify restricting to one universal machine when there are many others that we could have chosen, right? What we need is some vindication, something like some evidence that this is a fairly stable notion across choices of universal machine. Kolmogorov, again, amazingly saw this and put this in the 65 paper. So he proved two theorems. The first one called the Optimality Theorem. And this is a quick consequence of how we code our universal machines. Take a universal machine U, then for any Turing machine M, there is some constant C that's independent of our string S, sigma here. The complexity, I'm putting U here to be very, very precise. The complexity of sigma with respect to the universal machine is at most the complexity with respect to my other machine M plus this C here, which is the bits that I use to simulate M with my universal machine. So there's just complexity only, I'm kind of increasing the complexity just by a finite number of bits, but this is independent of sigma. So if sigma is a massively long string, this constant here will be immaterial. So that's the optimality theorem that Kolmogorov proves. And then from this, he derives the invariance theorem. Now pick two universal Turing machines, any two universal Turing machines. Then there is some constant, which is derived from the optimality theorem, right? It's just the maximum of two different constants from the optimality theorem that allows us to show that the complexity values assigned with respect to one by one universal machine compared to another, those two differ by at most a constant independent of the string we're considering. So asymptotically, two universal machines behave the same for all practical purposes. The values they assign to strings aren't the same, need not be the same, but if they differ, they only differ by a fixed amount. Okay, so that's what in our field often we use as justification of the restriction to one universal machine. When we extend to randomness for infinite sequences, the definition is completely independent of the choice of machine in a way we can define a random infinite sequence for a universal machine or any other one, then the class of random sequences never changes. So there's some stability that arises from this. Now, in the case of finite strings, we have to be more careful. And that's where I say here, this doesn't completely resolve the worry. There's still a little bit of, this allows a little bit of vagueness to creep into the discussion here. Sorry about that. Let me get this. I shouldn't have this here. Okay, going back. Okay, so now let's talk about trying to define randomness. So since there's a Turing machine that is the identity machine I had mentioned earlier, this gives us an upper bound for complexity. Every string has complexity at most its length plus a little extra constant, which is given by the index of the identity machine, right? The universal machine definitely can simulate the machine, which on input sigma, output sigma, but it can possibly do better. So every string's complexity is bounded by its length plus, whatever index, if this is the 83rd machine, then I'm looking at 83 plus 1 extra bits to code that. So we have a nice upper bound for complexity of strings. Now let's try to think about strings whose complexity is at least their own length, not at most their own length. So if I'm thinking about for a fixed length n, how many strings of length strictly less than n there are, there's a counting argument. Well, for strings of length n, how many strings of length strictly less than n are there? Well, there's one string of length 0, 2 strings of length 1, 4 strings of length 2, and so on. And so if I add up all the number of strings of length strictly less than n, I get 2 to the n minus 1. So if I'm mapping to each string of length n a string that is strictly less than that, I will leave a string of length n out. There will be one string that doesn't get hit, at least one string that is not obtained in that way. So that string, its complexity will be at least as long as its length, because I've used up all my shorter lengths. So there's always going to be at least one string which has complexity larger than itself, regardless of the machine that I choose, right? The universal machine that I choose. So I'm always going to have a string, and this is what we'll call an incompressible string. We can do a little bit more than that, because I think having one string being incompressible doesn't seem to be that much. So now let's fix a constant c, and let's consider strings whose lengths are larger than c. Okay, does it make sense to do this when c is the lengths aren't larger than c? And consider strings whose complexity is at most the length minus c. Any input to the universal machine that gives me a string sigma that satisfies this, the input has to be at least the length of sigma minus c bits long, which means I can't compress sigma by more than c bits. I can't find something much shorter than sigma that yields sigma as output. Okay, so we'll call these strings C incompressible. So here I think of like 10 incompressible strings of length 100, for instance. And now if I do a similar counting argument, I get this formula that tells me at least how many C incompressible strings there are. Okay, I don't want to dwell on this formula. Let's just plug in some values and see what we get. If I am looking at, say, strings that are 1 incompressible, at least half of the strings of a given length are 1 incompressible. At least 3/4 are 2 incompressible. At least 1 minus 2 to the minus c are c incompressible. That is a big number. So for instance, I don't care really about the length 100. How many 10 incompressible strings are there of a given length? That is 1 minus 1 over 2 to the 10. 1023 over 1024. 99.9% of strings of a given large length are 10 incompressible, cannot be compressed by more than 10 bits. Okay, so we have lots and lots of incompressible strings. They're easy to find. How do you find a 10 incompressible string of length 50? Toss your coin 50 times, and with a very, very, very high probability, you're going to obtain one of these. Okay, now let's define randomness. And good news, we can define randomness. Bad news, we can only do so here in a vague way. So we'll say that a string is random if its complexity is roughly its length. Wait, roughly? What is roughly here? Well, that depends on what level of C incompressibility we think is good enough for randomness. maybe all the one incompressible strings are random, but then, well, why not take the two incompressible strings, right? There's some vagueness going on here. So there isn't an exact notion. And for practical purposes, oftentimes in, say, combinatorial problems, if we want to use incompressible strings to stand as a proxy for kind of classically random ones, you can just pick a machine, a universal machine, pick a large, or a sufficiently large C, and the C incompressible strings will function for all practical purposes as if they were random. They will satisfy certain kind of stochastic properties that allow us to prove certain theorems. So here we don't need to know exactly how random we need our strings to be for certain purposes. If we want to say, here is an exact definition of randomness, pick this exact C, that seems very problematic. Okay, so the C determines what counts as random. And again, for practical purposes in the field, we can get around that because we don't need to have a specific C to do the work that, in improving theorems about incompressible strings, many choices of C would suffice. But there's also a problem if you're trying to pick out like the random strings just with respect to the choice of universal machine, despite optimality and invariance. And here's the issue, here's the problem. The invariance theorem says that the complexity values assigned by two different universal machines differs by at most a finite amount. But even in that little wiggle, that small amount of variation, we can really make weird things happen. So for instance, you can pick your favorite string. Maybe Demir has his favorite string. I can find a universal machine that will make Demir's string be incompressible. And I can find a second universal machine, which I hard code into the universal machine and make it as compressible as possible. Now, I can only do this for a finite number of strings. I can't do this for infinitely many strings. But at the level of individual sequences, the choice of universal machine can actually determine whether or not we count this specific string as random or not. Someone in the chat? Oh, good. Demir, oh, I see Demir has a favorite string. Good. So this is something that one might call, I call in the paper at least, the instability phenomenon. And I give a more precise characterization of what instability in this context amounts to. And it's defining a notion in terms of a parameter that under which modifications of that parameter causes the property in question to no longer hold. Okay, so there's something about that hasn't really been identified explicitly or formally as some sort of context, some sort of parameter dependence, but the notion of random sequence here is going to be dependent on the level of incompressibility we choose, the choice of universal machine we choose. So at least in this point of view, a collection of strings as random, that's not a stable notion, because we can modify what we take to be incompressible, we can modify our universal machine, and that might give us a different extension of kind of random sequences. For, again, practical purposes, this doesn't hurt a lot of what gets done in the field. But if we're trying to say we have a notion that picks out a unique notion of randomness in the context of finite strings, we have to be much more careful. I think that's much harder to claim. There has been some work, people try to find a notion of natural universal machine that maybe allows us to say, this is the right notion, this is the right universal machine, and from this we get a better collection of random sequences. But I think that work by and large has not been successful. Okay. So this is what I guess I have already said here. There's some stability with once we make choices of our parameters. So I'll just say quickly here, for instance, having choose a universal machine, having choose a level of incompressibility, you can show, Martin Loaf did this in a paper that was soon after Kolmogorov's, that finite strings that are C incompressible satisfy statistical properties up to a certain level of significance that is determined by those choice of parameters. So there's some sort of statistical regularity that emerges even having made those choices, kind of, yeah, in a way that I'll say a little bit more about near the end of the talk. So once we fix the choice of these parameters, statistically speaking, a lot of the properties that we'd want to have satisfied of random objects are in fact satisfied. Okay, let's move on to Chaitin's theorem and how he interprets that. Okay. So there's a lot of more detail one can go into. The literature on this often doesn't take any care with how we represent statements of complexity in arithmetic. If we're gonna, Chaitin's theorem really is gonna require us to say statements about the Kolmogorov complexity of strings in arithmetic. And since those statements are really statements about halting computations of the universal machine, these are sigma 0, 1 statements. So true sigma 0, 1 statements turned out to be provable in very weak theories of arithmetic. So Robinson's Q, right? We have sigma 0, 1 completeness. So all we need to do is to figure out a nice way to encode those kinds of statements. And I don't really go into any detail here. I don't want to do that. The literature, even in the paper, Chaitin stuff and the paper in 2013, they just assume that there's some way of expressing those statements, but they write down the Kolmogorov complexity of sigma in as if it were a statement of arithmetic, but it's not a statement of arithmetic. We have to represent Kolmogorov complexity and so on. So what I have is and I'll just kind of skip the details. There is, for any statement that the complexity of sigma is greater than or equal to a given value. So complexity of sigma is greater than or equal to n. There is some formula in arithmetic we can write down. So whenever I write phi sub c, and then I have the pound sigma n, here I'm representing sigma as a natural number. So I have to code my string as a natural number. So these are just a proxy for statements in arithmetic that say the complexity of sigma is bigger than n. Okay, so there's a way of doing this in a way that it's for statements for which this is true. This means that the universal machine on any input, if it yields sigma as an output, the input must have length greater than or equal to n. That's a true statement about some strings, right? This is just a statement about Turing machines. There's some formula for which that holds in arithmetic. So kind of sweeping aside issues of coding and representation, which in these papers on this, we kind of just assume that the similar kind of machinery that Gödel went through in his 31 paper, that's in place, right? So we can now state Chaitin's theorem. Okay, so I'll just assume that I have a way of formalizing statements of Kolmogorov complexity. I want to be able to say in arithmetic, this string sigma has complexity bigger than n. That's all I need. And then one other condition is if I have, so my theory T is going to be, I should say, computably axiomatizable and extends Robinson's Q. So Robinson's Q, very weak theory of arithmetic. This is just the base assumption for being able to do enough arithmetic, the base assumption for the original Gödel incompleteness. So let's say I have one other assumption. I want my theory to be C sound. And that is that if my theory proves that the complexity of sigma is greater than n, it's really the case that the complexity of sigma is greater than or equal to n. So I don't want this thing to prove statements that turn out, complexity statements that turn out to be false. Okay, so all I am doing is saying I want a theory of arithmetic that can prove complexity statements, and whenever they prove complexity statements, in fact, they prove the ones that are true, right? Which Turing machines halt and only give long inputs to this output here. Like that's a fact about Turing machines outside of like different, that's like in the standard model of arithmetic. That's just true of Turing machines. Okay, so here's the theorem that Chaitin proves. Let T be computably axiomatizable and C sound that interprets Q. Then there's some natural number n. Okay, there's some number n, so that my theory cannot prove of any string that it has complexity above n. Okay, there's always some threshold, right? N might be 10 million, right? For each theory, and kind of making some other assumptions about how I'm representing my formulas, but I'll say that in a second. There's some number, and I cannot prove, so some number 10 million, my theory cannot prove that any string has complexity above 10 million. Now there are strings that have complexity above 10 million, but my theory can't detect that. Okay, so piano arithmetic has a threshold on the strings, like it can only prove finitely many true statements of these kind of complexity inequalities. It can only prove finitely many. The complexity is, if any string has complexity bigger than some number, like piano arithmetic for that fixed number can't prove that that's the case. So now Chaitin's very excited, right? We get infinitely many statements that are true, but can't be proven by our theory in one fell swoop. So this is that claim. There's some threshold n, T can't prove of any individual string that has complexity greater than n. Okay, so that's the theorem, which is a really remarkable theorem. I think for the interest of time, I'm not going to go into the proof sketch of this because, I mean, this is the proof sketch is one slide, but I want to be able to get to further stuff. So if there's interest later on, I'll do it. It's not too complicated. So I kind of need one idea. So I'll just say a little bit. The idea is this. I want to build a machine that can enumerate theorems of my theory. And so if Chaitin's theorem doesn't hold, I can enumerate theorems that are expressing complexity statements, and I can enumerate theorems expressing complexity statements where that complexity that's showing up in the statement is getting arbitrarily large. And now, because my machine can enumerate, I mean, basically I want my machine to find complexity statements that are provably true of strings. And if it finds such a thing, a sufficiently large one, it will output that string. And the trick is, in virtue of that enumeration of theorems and then finding a string that has kind of a provably high complexity, that very process can be done with a short input, which is much lower than the complexity that's given by the statement. So if I can prove statements of this form with unboundedly large n here, I can find a very short input that leads to a construction of that sequence by just enumerating theorems. And the input that does that is much shorter than the threshold here. Okay, so there's essentially, it's, some people will say this is a formalization of Berry's paradox. We say something like the number definable, the first number not definable in 20 syllables, but that very number is definable in much fewer than 20 syllables. And so this is in a sense, a proof theoretic analog of that paradox. We say the first number who can, with proof that is, or the first number whose complexity statement, is much, how do I say this? The first number for which we can prove that its complexity is much greater than n. But if there is such a number, we can give a complexity, we can construct it and show its complexity is much smaller than n. Okay, so that's a very puzzling approach, and really it corresponds to somehow the proof mechanism being enumerable here in arithmetic. That really nicely aligns with constructions of Turing machines. Okay, more on that in a little while. Okay, so there's the Chaitin's theorem. The interpretation. If one has 10 pounds of axioms and a 20-pound theorem, that theorem can't be derived from the axioms. So now Chaitin wants to say, well, the value n for a given theory, the threshold n there, beyond which we can't prove complexity statements, that's something like intrinsic to the theory that measures the information content of the theory. And so that is the size, the weight of the axioms is given by that number somehow. But the theorems themselves have weight, right, somehow greater than that. We can't prove those. Okay, it's kind of hard to make this precise. I attempt to in more detail in the paper. So this value, this threshold for each theory, there is an n. We can't prove complexity statements above, for strings that have complexity above n. That number is somehow a measure of information content. Any string, Chaitin claims, that has complexity higher than this information content itself has information content, like the string itself has this kind of information content. Okay, so this is at least what he wants to claim. So that's the way he interprets this. This is like a measure of the complexity of a theorem. Of a theory. Panu-Rada-Chaitin, this is von Lembalgen. Von Lembalgen does amazing work in showing this is just absolutely false. So he does the following. He builds universal machines so that for one machine, this constant with respect to piano arithmetic is much smaller than the constant for ZFC. But then for a second machine, the ordering goes in the exact opposite direction. Okay, so this constant can't be something which is intrinsic to a theory, because we can just change the universal machine and completely destroy the ordering for one machine, right, by switching over to another one. So this is why I think this is fairly decisive. There's a problem here, right? these numbers are completely unstable. As we change the machine, we can cause the ordering of complexity by, intuitively we would assume PA is a weaker theory than ZFC, but now that weakness and strength doesn't get tracked at all because we can change our machine and get a completely different answer, a completely different kind of outcome. Okay, so that is like it's a clever theorem, but the interpretation of something like the information content of a theory doesn't work. There's quite a bit of work people trying to give alternative measures of information content of a theory. I don't know if they all similarly fail. It's an interesting endeavor, but I think that Chaitin's his approach falls flat. So now I want to tell you about this new approach that I think is promising. So let me just jump to that couple of results that would suggest that Chaitin's undecidable statements maybe have some sort of priority over other undecidable statements. Okay, so I'll give you a couple theorems here. So in this paper, axiomatic power of Kolmogorov complexities, Laurent Bienvenu, Andrei Romashchenko, Sasha Shen, Antoine Taveneaux, and Stan Vermeeren, so mostly researchers in France, they prove a couple of really interesting results. So here's the first one. Suppose I take piano arithmetic. Now you can do this in a more general way, but they just do this for PA. I take piano arithmetic and we add to it all statements of the form that are true. The complexity of sigma is greater than n. Complexity of sigma is greater than or equal to n. So I'm going to expand my theory by adding all true complexity statements. Then they show the following. This is pi 01 complete. For every true pi 01 statement in the language of arithmetic, PA star will prove that statement. So for instance, the sentence that, the Gödel sentence that Gödel identifies in his 31 paper is a pi 01 statement. It's a universal statement. It's a universal quantifier followed by like an atomic formula in the language of arithmetic. You can derive the Gödel sentence from the theory that expands PA by all true complexity statements. Okay, so if Chaitin says there's something special about his statements, this looks like, yeah, every true pi 01 statement, including like the ones that Gödel has identified, or if we're doing more complicated iteration of the Gödel phenomenon, and we get some sequence of true undecidable statements in that way, this theory captures all of those. Okay, so I guess Turing's work on ordinal analysis of theories in 1939 has some sort of like sequences that yield a pi 01 complete theory of arithmetic. This does it in one fell swoop, not by doing some sort of iteration of the Gödel phenomenon, but just by adding all of these complexity statements. So this suggests there is some proof theoretic strength. Maybe there is something like a proof theoretic priority that these statements somehow show how other undecidable statements can be derived. Okay, now I want to push a little further, and this I think is this is a very Sasha Shen sort of move in my field. Shen is very creative. In this paper, they define this a measure of complexity for pi 01 statements. Okay, this is a very unexplored area, even formally. Oh, I see the chat showing up here. What's the good? Oh, there's a crying. Okay, Demir understands Sasha Shen. So here's what I want to do. For a given pi 01 statement, I want to associate a string. And this string will be a string that satisfies this property. So maybe there are more than one string that has the case. My pi 01 statement is a universal statement. And I want to look at a string sigma for which PA proves phi holds if and only if the universal machine on input sigma diverges. So you might be asking, what is this? Well, you can think of the universal machine on input sigma as looking for a counterexample to this universal statement. And if it fails to find a counterexample, then the computation will diverge. So for true pi 01 statements, there's going to be some string, strings for which this is true. That there's a way of representing computation divergence as a pi 01 thing. So this is universal enough to make this kind of representation. For a false pi 01 statement, you can just find any sigma for which the universal machine diverges. So this is it's only an interesting measure of complexity for true pi 01 statements. And now let's define a notion of Kolmogorov complexity of a pi 01 statement. It's the shortest such sigma that is something like the instructions to look for a counterexample that is never found, right? That's like, it witnesses that there is no counterexample to my universal statement. Okay, this is a very clever move. And from this, now we can associate to Pi01 statements in arithmetic a numerical measure of complexity. And this is the theorem that Shen and Bienvenu et al. Prove. And I think this is like my favorite theorem in the paper. For each natural number n, there is a string sigma n, and it's in fact of length n, with this property. If I add to piano arithmetic just the statement that this string sigma n has complexity greater than or equal to n, I can derive all true Pi01 statements with this new notion of complexity being less than n modulo a constant. So now, instead of having Pi01 completeness, all complexity statements, if I add those to my theory, allow me to prove all true Pi01 statements, I can do this at a much more fine-grained local level. There's a sequence of special complexity statements that somehow govern, like from those, I can prove all lower complexity Pi01 statements along this kind of sequence. So now I have what you might call like a local Pi01 completeness. So I get Pi01 completeness kind of along this sequence, kind of chunk by chunk at a time. The union of all such things gives me full Pi01 completeness, but I can freeze it at a finite level and see the proof theoretic strength of just one of these formulas is enough to recover all lower complexity Pi01 statements modulo some constant, which depends on choices of machine and something like this. But this is still resistant to the instability, this kind of instability problem I raised before. For each choice of universal machine and how we code represent these notions in arithmetic, we will always find such a sequence sigma n of formulas that witness this property. Okay, so this is a really neat result. And this also looks like we have something like a measure of strength, right? In the paper, I do a little bit of work in the appendix to prove some theorems that they weren't teased out in this paper about the complexity of these things, but there's still quite a bit we don't know. We don't know quite a bit about which sequences could possibly play this role. This is fairly a wide open area. Okay, so now we might be tempted to conclude from these theorems that there's a sense in which Chaitin's undecidable sentences somehow control, even uniformly control, proof theoretically, other undecidable statements. I can derive lower complexity statements from this special sequence, or globally, I get Pi01 completeness. All universal truths can be derived from just these complexity statements. But there's a couple of problems. First of all, this only works for Pi01 statements. And we can find undecidable statements in arithmetic with higher complexity. The Paris-Harrington theorem, right? If you're into combinatorics, Ramsey's theorem, like some folks at UConn are, then you know these things are these are Pi02 statements. They're for all there exist statements. And Chaitin's theorem has no bearing on this. Now, here's a hint or an idea. Then let's define a notion of complexity for Pi02 statements in terms of totality of machines. That's something that was explored in Antoine Taveneaux's dissertation, just a tiny bit, but it's not something that anyone has pursued. And moreover, this is only applicable in the context of piano arithmetic. But you know, the incompleteness phenomenon occurs in much larger theories about, think about second order logic. Second order arithmetic has its own set of problems, and this doesn't speak to those at all. So this can't possibly be the source of incompleteness. At best, it's a source in a very constrained setting in arithmetic with respect to just Pi01 statements. Hey, maybe that's good enough. Maybe we can vindicate Chaitin's interpretation just in that kind of restricted, very restricted setting. But the problem is that also doesn't give us ultimately something new. And how do we see that? Okay, there's a little computability trick going on here. If you look at these sigma n statements, these strings, which now, the complexity that the statement that the complexity of sigma sub n is greater than or equal to n can prove all statements of complexity lower than n. I don't want to go into the details here, but the key is that these things allow you to bound the number of steps to solve an initial segment of the halting problem. Okay, so there's something like very clever that's done in this paper. These sigma n's, it's I'll just say, what is this? It's the first string of length n with complexity greater than or equal to n. Now, if you know that string, if you have a string if you know that this is the first string of length n with complexity greater than or equal to n, and here I mean first in the lexicographic order, then I can watch all strings kind of to the left of this string, knowing that they're all going to have complexity less than n. And I can watch until I see witnesses, the universal machine, giving me inputs of all inputs less than n to yield every possible string to the left of this thing. And the stage at which I see that happening gives me some special time bound. And it's a time bound that tells me how long I need to wait to see all strings given to the universal machine to halt. If I give it a short string, kind of modulo a little bit of a constant, a string of length less than or equal to n, either it halts within that time bound, or the computation will never halt. So these strings here, the complexity values of them have kind of proof theoretic strength because they're really encoding finite chunks of the halting problem. So it isn't really about complexity, it's about recovering something corresponding to the halting problem that allows me to have this proof theoretic strength. And moreover, I want to really justify why that's the case. There are other choices of complexity statements that do not have this proof theoretic strength. In the Bienvenu et al. Paper, they show that you can find 99% of the strings. There's like these asymptotic results that tell you most choices of strings of length n along a sequence in this way do not yield this proof theoretic strength. It's only the ones here, seemingly, we don't know this exactly, but we have it seems to be the case that you have to have these special ones from which we can recover time bounds for the universal machine to halt. Those are the ones that have the proof theoretic strength. So really, what's governing the proof of all these pi01 statements? It's the halting problem, which we already know to be pi01 complete. Information about the halting problem allows us to prove true statements in arithmetic, pi01 statements in arithmetic. So it's a clever disguise, but there's nothing like conceptually about complexity here. It really seems to be something about recovering information from the halting problem that has that proof theoretic strength. So we really haven't learned anything deeper about undecidability or incompleteness than what we can find. We've essentially repackaged information about the halting problem. Okay, I want to just say a little bit more to give an alternative interpretation. I know I'm short on what I want it to be, but let me just say, I'm going to skip a few slides because I would like to get to the discussion here. What I think about these theorems is that they tell us something about a formal trade-off between weaker and stronger definitions of randomness. So instead of going through all my slides, let me just tell you what I have in mind here. So Kolmogorov complexity is a measure of complexity, or essentially a measure of randomness given in terms of all Turing machines. And equivalently, you can show, and I've mentioned this before, that this has to do with, it's equivalent to a characterization of randomness with respect to statistical tests. And these statistical tests are given by computably enumerable sets. Now, if you know some computability theory, you know that computably enumerable sets need not be computable. So you might think, let's consider a notion of randomness that behaves statistically random, not with respect to all computably enumerable tests, but all computable tests. So now I have fewer tests for randomness for my sequences to pass. But if I have fewer tests to pass, then I have more sequences, at least a priori, that will satisfy or pass these tests. I'll have a larger notion of randomness. So as I vary the strengths of my tests, or I vary the strengths of my machines that I'm doing compression with respect to, I can get kind of smaller or larger notions of randomness. At an extreme case, I might use a finite state automata for my compression. And so now this is a very constrained notion of compression. And so more sequences will be counted as incompressible because I have a weaker notion of compression. Or I could say I want to do all Turing machines, or maybe all Turing machines equipped with such and such an oracle. And now this is, I'm broadening, I'm making more things are going to be compressible because I'm giving myself more strength, more computational strength. And so fewer tests, fewer sequences will be counted as random because I'll have more tests to pass. I'll have a more demanding notion of randomness. Now, in that world, there's a trade-off because, for instance, with respect to, say, incompressibility that we've seen, there are computational limits to working with such a class. I'll give you an example. Suppose I would like to find a computable function that outputs only C incompressible strings. Just give me examples of C incompressible strings. Right? That would be nice. Then I can always have, I don't care how sparse they are, I don't care which ones, just give me C incompressible strings. You can prove the following for any C. The set of C incompressible strings is immune. In computability theoretic terms, that means that it has no computably enumerable subset, which is equivalent to saying that there is no computable function that outputs a sequence of C incompressible strings. I mean, you can repeat the same one over and over. Of course, I don't have that in mind. So that if I wanted to be able to somehow access incompressible strings, if I want a notion of randomness that gives me examples that I can work with, incompressibility in the sense that we've been considering is too strong because I can't produce examples. Now you might think, well, why would you ever want examples? Well, for certain purposes, maybe I need random strings to give me, to mix up, for randomization for whatever, I'm performing a statistical test and I want to randomize the order of something. Then maybe I need some notion of pseudo randomness that I can access so that I can use that to like mix up the order of experimentation or something. For scientific purposes, I may want a notion of randomness that I can reproduce, which seems crazy, right? If it's reproducible, it doesn't seem to be random. But often when we have like pseudo randomness, even in like computational games, it's done in terms of a seed that we use, and it allows for reproducibility. I think about like, there's something called a cross-validation in machine learning that often involves me randomizing my training set and my test set. And this is done with pseudo-randomness with a fixed seed so that we can reproduce this. Okay, so some uses of randomness, we just need to be able to give concrete examples of that. And so those notions would correspond to some much weaker notion of incompressibility, not in terms of Turing machines. Okay, so how does this bear on what we're doing now? And I'll just jump to it. The claim here is Chaitin's theorem shows us a trade-off, at least on one side. If we work with a sufficiently strong notion of randomness, we lose an ability, right? We lose the ability to formally certify randomness. Okay, so that's what I claim here. This is one way of kind of a gloss on Chaitin's theorem. What is certifying randomness? It's just a formal proof of the incompressibility of our string. So if we require our random strings be incompressible in the way that we have been, Chaitin's theorem shows that most incompressible strings are not provably incompressible. We cannot certify the randomness of those strings. Okay, so this is something like, I want a uniform notion of certification of randomness in a given theory. And I can't do it. Chaitin's theorem shows it can't be done. So here's how you might recast Chaitin's theorem. And this is a way that's completely independent of coding constants and everything. For any choice, okay, so pick your favorite theory of arithmetic that interprets Robinson's Q. For any choice of universal machine, any choice of L formula to represent computations with this machine, any choice of C for our level of incompressibility, at most finitely many C incompressible strings are provably incompressible in my theory. Well, now there's no dependence because I'm quantifying over those parameters. That's what Chaitin's theorem shows. We can't prove the incompressibility of strings at this level of compression. Okay, and you might think, well, how does this work if I weaken things? Let's weaken things. Suppose I look at a notion of compressibility with respect to time-bounded machines. So fix a computable function, and I want to define a notion of complexity with respect to that computable function T. What is this time-bounded complexity? Well, I use the universal machine and I look at the shortest input that yields my output sigma, but I can't use more than a number of steps bounded by t of the length of sigma. So this bounds the how many steps I run my universal machine. So this won't necessarily fully compress my string because I'm only running computations for a fixed amount of time. But this measure of complexity is computable. I can find a computable function that outputs time-bounded incompressible strings for whatever computable time-bound I want. And so in a lot of work on Kolmogorov complexity that you see in more of the kind of computer science world, it's often concerned with pseudo-randomness cashed out in terms of time-bounded complexity. And now if you want to formally certify the randomness, the time-bounded incompressibility of strings in a theory of arithmetic, you can do it. Theories of arithmetic can prove these things because these are facts that are computable facts. We're not using a notion of machine, which is somehow as strong as the proof system that we're working with. The machines are weaker than the proof system. And so I can't use the kind of trick that Chaitin uses to prove his theorem. I can certify the randomness of weaker notions, the randomness of strings with respect to weaker notions of compression. Okay, so that's the trade-off. On the one hand, if I want a very strong notion of randomness, then I may have to give up certain desiderata for my definition. I may have to give up the ability to, say, computably produce examples of incompressible strings, or the ability to certify the randomness of my strings. But if I, on the other hand, want the certifiability or the ability to computably produce examples, I can't work with such a strong definition. I have to opt for something time-bounded or given in terms of finite state machines or something at a much weaker level. Okay, so that I think is kind of a more full picture. Much work in our field is kind of playing off of different notions of strength and the consequences that follow from it. And I think that often doesn't get highlighted in that way. A lot of the work on theorems, work on definitions of infinite random sequence have this very property. You vary the strength of the definition and it yields certain consequences. The stronger the definition, the more computationally intractable certain things are. The weaker the definitions, then you have some other nice properties, but then maybe other trade-offs arise. So highlighting and charting these trade-offs is kind of what I've done in a couple other kind of very different papers. I'd be happy to talk about those as well. Okay, thanks very much for your attention.